First, I'll start by telling you a little bit about Romax technology, just in case you're not familiar with us and what we do. Our key industries are automotive and wind energy, and key businesses gearbox, bearing, drivetrain design, simulation and analysis. We were founded just over 25 years ago, and our software tools are used by most of the top automotive OEMs worldwide. Although we are a small company, we are global with offices across the world and particularly strong presence in the US and the Far East. This animation here that you can see on the slide is an automatic gearbox model built in Romax Designer. So next I'll just tell you a little bit about the R&D work we do here at Romax. It's a very important part of what we do. We invest more than 10% of turnover in R&D every year. So this is just a brief overview of the current and recent projects. So this one is about improving the efficiency of a heavy-duty truck axle funded by Energy Technologies Institute. The Odin project is about the effect of vibrations in the motor of an electric vehicle exciting normal modes in the gearbox and vice versa. It's very important to consider both components together rather than in isolation. EMAS is an aerospace project. It's about lightweighting actuators without compromising on strength and durability. And MagSplit is an application of the Romax drivetrain simulation methods that I'll talk about in this webinar. ProtoDrive is a project that uses the same simulation methods, but also including efficiency models of drivetrain components, so the engine, transmission, battery, electric motor. Romax has sponsored a PhD project at Loughborough University, which involves gathering real-world driving data from a Toyota Prius vehicle, and that data is being used as a case study for our simulation tool in the ProtoDrive project. Dynamics is also a key theme for Romax R&D. In Orchestra, we're building mathematical models with exactly the right amount of detail for the phenomenon under investigation. This one is a control project collaborating with Gamma Technologies. We're also looking at bearings. We're trying to understand the underlying physics of how the different components interact. We have some wind turbine projects as well. The RGF project is looking at a wind turbine drivetrain, in particular what effect excitations from the gearbox have on the generator and vice versa. The purpose of the DEC project is to reduce the overall load on the wind turbine by controlling the pitch of the wind turbine blades individually rather than all moving at the same time. And finally, WindDrive is about developing a generator technology from a small-scale demonstrator up to a full industrial scale. So that was a brief overview of some other R&D projects that we're working on within Romax. Now I'm going to talk a little bit about the motivation for reducing carbon. The motivation isn't just an altruistic desire to save the planet, though of course that's very important as well. There are actually financial incentives for cutting carbon emissions. Current Euro 5 legislation mandates a fleet average carbon emissions of no more than 130 grams of carbon dioxide per kilometre driven. In 2013, we just about met that target. However, the Euro 6 legislations that are coming in from 2020 onwards has a stricter limit, 95 grams of carbon dioxide per kilometre. And there are consequences for manufacturers that don't meet these targets. They get fined €95 per vehicle per gram. So I did some number crunching to see how much this adds up to. If you take the number of cars produced in the UK in 2013, multiply by €95 per vehicle, and multiply that by the difference in emissions between 2013 levels and the 2020 targets. If there are no improvements in carbon emissions, the fines add up to a substantial amount, nearly 5 billion in the UK and over 50 billion in Europe. So for large manufacturers, it's well worth spending a small percentage of that money on R&D in order to reduce carbon and avoid the fines. With vehicles, you can't just pass the cost on to the customer. The market is very sensitive to price, so the only real alternative is to reduce the carbon emissions. But there are lots of different ways of doing that. Hybrids and EVs are increasingly an important way to achieve that. As you can see from this diagram on the right, the number of available models of hybrids and EVs has been increasing dramatically over the past decade or so, and this trend looks set to continue. So to address these issues, Romax has developed a drivetrain simulation methodology. The idea is that it can scan across a spectrum of different drivetrain layouts, going from pure electric to pure engine powered and looking at lots of different options in between. Hybrid drivetrain design is a complicated problem. There are lots of different layouts for your vehicle, lots of options for your component sizing and specification. Overall, there are many degrees of freedom in design and control. With hybrids, it's not just a case of power being generated by the engine and going directly to the wheels to drive the vehicle. Hybrids are more complicated than that, and the fuel consumption is very sensitive to how the vehicle is controlled. For example, when you switch between pure electric driving and using engine power, at concept design stage, it's more important to be able to look at all of these options quickly than to do very detailed simulation, as long as the model fidelity is sufficient to enable engineering judgments on how to optimize your vehicle. Traditional vehicle simulations tend to be computationally intensive, which means in practice you don't really investigate the whole of the design space. As well as the design of the vehicle itself, it's very important to consider the driving conditions. For example, if you're driving in the city centre, you're probably going at low speed, accelerating, decelerating, starting and stopping, slowing down for roundabouts, stopping at traffic lights. That's a very different requirement to driving on a motorway when you're going at high speed, not accelerating or decelerating very much. If you design your vehicle with only one drive cycle or set of driving conditions in mind, you probably find that your design will perform less well under different driving conditions. So you can see from this graph here, this shows the difference between measured fuel consumption from various different sources and the manufacturer quoted figure. The manufacturer quoted figure is based on only one drive cycle. So you can see not only is it a very big difference, but this discrepancy is increasing rapidly with time. It's becoming more and more of a problem. Most drive cycle simulations work in the time domain, which means that the simulation runs through the drive cycle, analysing one time step at a time. With that kind of simulation, the time that it takes to run the simulation is proportional to the duration of the drive cycle. So in this example here, if you want to run your simulation over 3 different drive cycles, then you have to add them together, and your simulation could take 3 times as long to run. So in practice, it means that vehicle designers don't consider all the different drive cycle options, which runs the risk of coming up with a design that's not robust to variations in driving style. Romax takes a different approach to drive cycle simulation. We use a statistical approach in which the drive cycle is represented as a series of speed, acceleration, operating points, rather than a profile of speed against time. And the advantage of this is that if you add multiple drive cycles together, you still have a series of operating points in speed and acceleration. They're not taking up a wider operating space, so there's no time penalty for adding more drive cycles. So our simulation uses a simple matrix calculation over this speed acceleration operating space, rather than doing a separate calculation for each time step in the drive cycle. And the advantage of this is that matrix calculations are faster. We use a backwards simulation method, which means we start with the force needed at the wheels to fulfill the drive cycle, and then track back to calculate the fuel consumption, rather than the other way around. The backward simulation method is simpler and runs faster than forward simulation. It does have a limitation in that it can't model the driver behaviour quite as accurately as forward simulation, but it is still good enough for concept design. So we start with the tractive force here at the wheels, and then track back through each component in turn, calculating component speeds and torques and powers with simple matrix calculations. And then when we get back to the engine, from the speed and torque matrix of the power coming out of the engine and a fuel flow rate map, which is an input to the simulation, we can calculate the total volume of fuel consumed. Hybrids usually have more than one operation mode. Like here is an example of a parallel hybrid. You can drive it electrically, which means you use battery power to drive the vehicle where the engine is switched off. Or you can drive it in hybrid mode, which means you can use power from the fuel tank and also power from the battery at the same time. The Romax simulation automatically selects the propulsion mode that gives you the best overall system efficiency for each speed acceleration operating point. The most time-intensive part of the simulation is the matrix calculations I described on the previous slide. And that part happens outside the optimization loop. The optimization is just choosing which of the pre-calculated states has the best efficiency. So that optimization loop runs a lot faster. It is usually desirable to keep the battery state of charge at the end of the drive cycle the same as it was at the beginning. This is useful to enable a fair comparison between different kinds of vehicles or different drive cycles. The hybrid propulsion mode here is broadly charge positive, whereas the electric mode tends to be charge depleting. So we can balance the battery state of charge by adjusting the proportion of time that the vehicle spends in these two modes. The way that we do that is to define a power threshold, which is represented by this black line on the diagram. So by changing the value of that power threshold by which you switch between the two propulsion modes, you can allow the control strategy to reach a charge neutral state. I did mention earlier that a statistical simulation method is a lower fidelity model than time domain simulation. We have done some verification comparing our statistical simulation methods to a commercially available time domain software just to see what the differences were. And as you can see from the graphs here, we have very good correlation in the results despite the limitations of the statistical domain. And most importantly, the trends of the results are the same. The trends are what's most important when you're trying to decide how to optimize your vehicle or in which direction you should change a parameter value. And you can see from this graph on the right that the trends are the same for statistical and time domain simulation. So in exchange for a very slight reduction in model fidelity, you get a dramatic increase in speed. So now that I've outlined Romax drivetrain simulation and how it works, I'm going to talk about a project where we've applied these methods. This is the ProtoDrive project. We're about 2/3 of the way through. It's funded by Innovate UK, and the aim is to build an integrated tool for rapid concept design of hybrids and EVs. The consortium consists of Romax Technology, CMCL Innovations. CMCL are an SME based in Cambridge. They have expertise in engine simulation and modelling. And the third partner is the University of Sheffield Electric Machines and Drives Group. This project is an evolution of the simulation methods that I've already described. Rather than just taking component efficiency maps as an input to the simulation, in ProtoDrive we have developed our own component efficiency models for the engine, transmission, electric machines, battery and power electronics. Well, these component models are integrated into our drivetrain simulation so that we can calculate the component efficiencies as the simulation is running. It's very important that we're a multidisciplinary team because typically the subsystem models are not always well integrated or of equal fidelity. So that's an issue that we're trying to fix. Our first case study in the ProtoDrive project is based on a 2004 Toyota Prius. We chose this vehicle because it's quite an interesting drivetrain with different power flow paths. So here you see the red path is where power is generated by the engine and goes straight through the drivetrain to the wheels. That's the power path that you would have in any conventional vehicle. The blue power path here is where power from the engine goes through MG1 acting as a generator, is converted into electricity, and then that electricity is used to drive MG2 acting as a motor, and that motor drives the wheels. This might seem like it's going a long way round, but the advantage is that it effectively decouples the engine speed from the wheel speed. Engines tend to have better efficiency when they're running at high speed, so with this arrangement you can have the wheels going at low speed and the engine going at high speed, which is more efficient overall. The green path here is electric-only driving mode, where the vehicle is powered by the battery through MG2, and also in the reverse direction, when the vehicle is decelerating, that kinetic energy can be captured and turned into electricity by MG2 acting as a generator, and then stored in the battery to use later on in the drive cycle. Here you see the efficiency maps for each of these components generated during the Protodrive project. The planetary gear set here splits the power between the engine and the two motor generators. We use a control strategy to determine how much of the power demand should come from the engine, how much from the battery, and we choose the power split that gives the best overall system efficiency. MG1 operates mainly as a generator, but can also be used for engine starting, and MG2 enables the electric-only driving mode and can also provide electrical boost while the engine is running, as well as being used for regenerative braking. So just to give you an indication of the simulation speed, the drivetrain simulation for this model runs in less than 10 seconds. And to run the entire simulation, including the component efficiency models and calculating all the efficiency maps as well, takes less than a minute. So now I'm going to show you some results from this case study. We wanted to find out how sensitive the fuel consumption is to changes in various parameter values, and most importantly, how does that sensitivity differ between different drive cycles. So these are the cycles we used. New European Drive Cycle is the legislative drive cycle for Europe. As you can see, it's not very representative of how real people drive. It has all these regions of constant speed, constant acceleration, constant deceleration. The second cycle is called Highway Fuel Economy Test. It is part of the US legislative cycle and represents driving on a motorway, so quite high speed, not accelerating or decelerating very much, not stopping and starting. We also looked at an urban drive cycle. As you can see, this is lower speed and a very starty-stoppy, higher accelerations and decelerations. So this graph shows how much improvement you get in fuel consumption over a drive cycle when the value of each of these parameters is reduced by 10%. And these different coloured bars represent the different drive cycles, and the purple one is a combination of 8 different cycles. So as you can see from the graph, different drive cycles have very different sensitivities, sometimes in opposite directions. So if you are only looking at one drive cycle to optimize your vehicle, that would lead to a different decision on what parameters you need to change in order to optimize your design, as well as a different decision about which parameters are the most important to investigate. And one more result from the case study. We looked at varying the values of the final drive and planetary gear ratios. So on the x-axis is the final drive ratio, on the y-axis the planetary gear ratio. And these contours here represent fuel consumption values, so lower numbers are better. And this cross here marks where the 2004 Toyota Prius lies in this design space. So under NEDC you can see that the fuel consumption is quite close to the optimum. With the urban drive cycle you get a very different result. The optimum ratios are over here to the right of the graph. With the highway cycle, you get the opposite result. The optimum ratios are way over here to the left of the graph. And running the simulation over our combination of 8 different drive cycles shows that the existing gear ratios are a good compromise between the different demands of these different drive cycles. So the key point to note here is that in mapping out a design space like this, we not only find out where the optimum regions are, but we can see the whole shape of the design space. And that's very useful if you want to come up with a design that's robust to small changes in driving style. So to summarise, the aim of a Romax drivetrain simulation is to investigate large numbers of designs quickly in order to map out a design landscape and narrow down the options. And a concept design stage, that is more important than producing a very detailed model that exactly matches the measured fuel consumption data. We have a PDF available with more information on the ProtoDrive project as well as Romax R&D in general.